Hey everybody, Mr. Ling here. Just wanted to go over classifying chemical reactions as promised. So tips and tricks to identify different types of reactions that you might see. This is something that you'll need to be able to do on the last module exam. So let's go through the different types of reactions that you might run into. First of all, here's the list. And you might take notes on this. You might have this in your notebook. I'm posting these slides as well, so you have them in slide form, but it might be nice to have a little reference that you can write some of your own notes on as well. But these are the main types: combustion, synthesis, decomposition, single replacement, double replacement, acid-base, and oxidation reduction or redox reactions. So let's go through what these look like and how to identify them. First of all, combustion reactions. What are combustion reactions? And you'll notice on my slides I've changed the color for each one because I like color coding stuff. And combustion, fire is orange, so I figured that works. So first of all, one clue is there's always oxygen involved. In order to have fire, you have to have oxygen. So if you see oxygen anywhere in the reaction, oxygen gas, that is, usually O2, right? You should think maybe possibly combustion reaction. Also, in combustion reactions, not always, but many times you get carbon dioxide and water that are produced. And that happens when you have an organic compound that is combusted. So an organic compound is something that's got like carbon and hydrogen and oxygen in it. Wood would be an organic compound. If you're burning something like a metal or something like that, then you probably won't get carbon dioxide gas. But having carbon dioxide as a product is another hint that it could be a combustion reaction. Example of this would be something like this here. We have C3H8 plus 5 oxygen molecules equals 3 carbon dioxides plus 4 waters and energy. That's another telltale sign you have combustion is when energy is produced, because if you think about it, when you burn something, you get heat, right? So that's another example. All right, so again, oxygen on the left, always. Maybe carbon dioxide and water on the right, depending on what's being burned. And you get something like this where you have energy produced. All right. Next is synthesis and decomposition. And I kind of group these together because they're kind of like the same thing forwards and backwards. Synthesis is basically just literally means coming together. So it's when you take two separate things, an A and a B, you react them and you get an AB, which is a different thing altogether. But it's combining those two into one molecule. An example of that would be combining 2 copper atoms plus oxygen to get copper oxide. And you might think, oh, wait a minute, Mr. Ling, there's an oxygen there. So is this a combustion reaction? Well, it's not really a combustion reaction because nothing's being necessarily burned here, I suppose. But because there is oxygen involved, you could classify it as a combustion. And remember I said before, with combustion reactions, you get water and carbon dioxide as a byproduct if you burn something organic. And in this case, this is a metal, and this is basically just rust. But I will tell you, this is also an oxidation reduction reaction, which we'll learn why later on. But for right now, we know definitely it's a synthesis reaction because you've got 2 separate things that are by themselves, right? They're not mixed with anything else. It's solid, pure copper, pure oxygen coming together to make one new thing. Now, decomposition, opposite, right? So it's breaking apart. It's taking what was one piece and now separating it into 2 separate pieces that are different compounds or elements altogether. So an example of that would be the electrolysis of water. If you take water and run an electric current through it, which hopefully I'll do in a demo on one of our virtual sessions, because it's kind of a cool thing to watch, you can actually split the hydrogen and the oxygen to form hydrogen gas and oxygen gas. So notice here, I've got one compound, which is water, which is a combination of two different elements. And we've split that into pure hydrogen and pure oxygen. So it's decomposition, taking one thing, and turning it into two things. Okay? All right. Single replacement reactions. So a replacement reaction is basically, if you watched the virtual session earlier, when you have the square dancing thing happening, when you have your partners kind of switching places, right? With two dancers spin, and the one spins off and grabs the arm of another dancer, and now they've exchanged people. Well, that's kind of what single replacement reactions do as well. We've taken two things here, and A and BC. BC is a compound, and B has tossed off C and has gone off by itself, and A has picked up C here to form AC. So C is basically kind of switched places, right? Switched partners. So basically one element changes the element it's bonded to, right? So it was A by itself, BC, now it's AC and B. An example of that in a chemical reaction would be like copper plus silver nitrate here. We have two silver nitrate atoms. Again, this is a balanced chemical equation. We learned about that earlier. And we've just switched roles. So the NO3 group, this kind of acts like one thing here. This NO3 group has popped off and has bonded with the copper to form, I think this is called cupric nitrate, which is kind of a weird term. But sorry about that. But at any rate, it's switched places. So the NO3 has gone from the silver to the copper. And then the silver is left all by itself. Poor silver. All right, so that's a single replacement. Only one exchange has happened, right? You can also have double replacement reactions. And a double replacement is exactly what it sounds like. It's a replacement, but two different things are switching places. So this kind of general form is you have two compounds, AB and CD, and they've just switched, and now it's AD and CB. Doesn't have to be in this particular order. You just have to notice that two elements are now bonded to two different elements in the products. So in this case, we have NaCl, sodium chloride, and AgF, silver fluoride. Those two have reacted, and the Cl has gone from the sodium to the silver right there. So we have to form silver chloride. And the fluorine has popped off the silver and said, you know what, I'd rather hang out with the sodium. So it's connected with the sodium there. So we've got two things that have switched places. The fluorine and the chlorine have both switched places, or you could say that the Na and the silver have both switched places too. But it's a double replacement. Two things have swapped. Okay? Acid-base reactions. So acid-base reactions are, you'll see a couple of different things with these, but we've learned about acids and bases. We know that acids are things that donate hydrogen, right? And bases are things that donate hydroxide or OH. And we know that the water molecule is a combination of OH and H to form H2O, or water. But in an acid-base reaction, the acid and the base react together and neutralize each other. You always get a salt out of that, some kind of a solid precipitate. A precipitate is just a solid, if you were to actually mix these things together, you'll see some kind of a solid form. It'll get cloudy. You'll see actual particles at the bottom of your beaker or whatever you're working in. And, I've got very little time left here to splice this together later. And you'll have water as another byproduct. So an example of this would be hydrogen chloride, HCl plus sodium hydroxide, which is NaOH. I think I showed this as an example earlier in the lesson too. To get NaCl, which is